name's Everett Minshall, and in today's video, we'll be looking at ARIMA and SARIMAX models for time series analysis. Specifically, we're going to be forecasting demand for a product from an e-commerce catalog. Time series has pretty unique challenges. It's not as simple as cleaning the data and throwing it in a model and you're done. So in today's video, by the end, you should have a pretty good idea of a pipeline structure that you can go through, the steps that you can go through to create a very robust model for your time series analysis. This is specific to retail product demand forecasting. So if you wanted to use this for a time series on, say, stocks, like I've done in the past in other videos, it might most likely would be a different process, but in this case, I think we'll have a really robust understanding of how to forecast demand for retail products, as well as other durable goods as well. So let's jump into the computer and we'll get started.
I also want to mention that if you hear some ambient noise, it's because my neighbors upstairs are extremely loud. The floor, for whatever reason, in this office building is like super thin. So I apologize in advance, but I think we'll be able to make do. It's early enough in the day that it shouldn't be a problem. So what we're going to do, I have the data loaded in my Google Drive, so I'm just going to mount that here in Google Colab, and then we're going to load it. And it shouldn't take too long. So yeah, looking at the data set here, these are our columns: invoice, stock code, description, quantity, invoice date, price, customer ID, and country. Now, invoice date is the column we're going to be using a lot, and I don't want to type out invoice date every time, so we're just going to change that to just date. And then we don't have a sales column, so we're going to create one by multiplying the price to the quantity. And the reason we want a sales column is because we need a column that represents our demand. And we could choose quantity, but I think since we have the price for each item, we can just multiply the quantity to get the total price on that invoice. And then that gives us a better idea of the demand. And you'll see here that that's exactly what we create here. We're just going to choose one item in our list. So I just chose this one at random. It's the bottom one here. You could do a little bit further exploration to see which one, has a more impressive time series line, and that'll make more sense as we go on. But for now, just picking a random item should work for us. So great, now we have a new data frame containing just one item in our inventory, and the quantity and the price and the sales for each day. Now, that creates a lot of redundancy. So I'm going to drop description, invoice, and stock code. And I could have dropped price looking at this, but when I was setting this up, I didn't think about it. So now we've sort of dropped the redundancy. We have information that's a little bit more rich. And before we get to further changing this data frame, I like to make a copy because we're going to be messing with the indexes. We're going to be doing a whole lot of stuff here. So I found just when you're working with a data frame where you're going to be messing with the index, it's best to just create a data copy so that if you need to go back, you don't need to restart your runtime. You can just reinitialize your variable from this starting point. So what we need to do is change this date here to a date time, because if we take a look at it, so if we take a look at our D types, what we'll find is that the date is an object, and we want to turn that into a date time. So the way that we would do that is just call that column pandas to date time, the column, and then we want to reformat the string so that it's a lesser resolution, because right now we have each day and what time of day that the sale occurred, and we don't need that information. There's probably a more elegant way to do this. I thought I could just, you probably don't need to include this date time part and just turn it into reformat the string as a date time, but when you reformat it, it turns back into an object. So then you have to reinitialize this date time. It's sort of a weird piece of code that I couldn't figure out how to get around. But you can see now that we've changed our dates here to just be each day. If we relook at our D types, you'll see that it's now a datetime object. So now that we're at this point, we're in a datetime object. What we want to do is take a look at sales per day, which means that we need to group our data frames together by the day, and then we need to sum up the sales of each day. So on 12/1, we need all of the total sum of the sales for January 1st, 2009. And then we need the sum of all the sales that happened on January 2nd, 2009, and so on and so forth. So one way we can do that is I just created another data frame, and we took our current data frame and grouped it by the date, date time, date. This can be a little confusing. So what we're doing here is we're saying take the current data frame, go to the date column or the date feature, use the date time function that we've imported, and use the date method to aggregate the sales, the sum of the sales, and then reset the index. And when we do that, we can then set that date as our index and take a look at our date frame. And this is what we get. So we have each day, and we get the sum of the sales. Now, this is fine. We've lost a lot of the information here: country, quantity, price, etc. But really, to get us started with the ARIMA model, we just need these two pieces of information, because we want to forecast what the sales is going to be by each day throughout time, across time, right? When you'll see later on in the video that we will add exogenous information, meaning that we'll re-add the price, quantity, and some other date history. That's mostly the important part, like holidays and weekends and things like that. And that'll improve our model. So for right now, though, just to train it and fit it, this is all we need.
At this point, what we want to do with our data frame is, if we were to take a look at the entire scope of our data frame here, we would see that we're missing a bunch of points, like weekends, holidays, things of that nature. So when we go to fit our model, we'll want those data points. And if we just think about it intuitively, if it doesn't show up in our transactions data here, it means that no transactions took place on that day. So we just want to record that. So what we'll need to do is extend the index of our data frame, add in those missing dates, and include a 0 value for our sales feature on that data frame. So one way we can do that is by creating a separate series of dates that encompasses the entire time frame of the dates that we're looking at with our transaction data. And then we re-index our data frame to include that series as the index and just fill in null values with 0. And we can easily do that with the re-index function.
So I just created a series of data from the beginning of our time frame to the end of our time frame in this data frame here at a daily frequency. So we'll do df data frame reindex with these dates, and then fill in the null values with 0. That's what this reindex method does. It's really handy. It took me forever to figure this out, but essentially we get what we're looking for. And you'll see here on 2009, January 12th, there were no sales. This row here would not have shown up in our previous data frame. So that's why we need this row here. We need this data point. So if we plot it, it should look something like this. Now, if you're using different data, obviously your line will look totally different than mine. But if we look across 2009 to 2011 of our product here, this is the level of sales that we get. Not the most interesting time series. Like I said, we could do something a little bit more robust where we didn't have all these blank spaces here. But for our purposes, it'll still work. So now we're on to step 2, where we're going to analyze this line here and understand the feasibility of our modeling. So in order for time series models to work, you want your time series to be stationary. And what stationary means at a very high level is that the average is constant and the variance is constant. In my research, it said that covariance doesn't depend on time, no trends or seasonality, but cycles can be present. So it's okay if there's covariance, but we want the variance to be constant. And one way we determine whether or not our time series model is constant is by using the AD Fuller test. So we can just import that from StatsTool. And we will take the rolling average as well as the rolling standard deviation of our time series. And then these two things here just plot what we've done. So AD Fuller just is the Dickey-Fuller test. The A stands for Augmented Dickey-Fuller test. I don't want to go too deep into the math here because it's not super relevant, but it's a package here that will help us test whether or not our line is stationary or not. As you can see, it's pretty stationary, just because there are a lot of days where there's 0. But regardless, if your line is less stationary or if you're working with data that doesn't look like this, or if you see a trend upwards, you know that it's not stationary. But it's always important to do an augmented Dickey-Fuller test because you'll gain a lot of information and you can definitely decide whether or not it is stationary or not. So now that we've defined our functions there, we can plot it. And as you can see, the red is the rolling average and the yellow is the standard deviation. If we look below this, we'll get the Dickey-Fuller test. Our test statistic is -4. P-value is 0.0002.
So specifically with the Dickey-Fuller test or the augmented Dickey-Fuller test, the p-value, if you remember in statistics, just determines whether or not we can reject our null hypothesis. So when we're talking about the Dickey-Fuller test, the null hypothesis is assuming that our time series model is not stationary. So when we get a p-value under 5%, which is sort of the standard critical threshold for our p-value here, it means that we have a statistic significance to reject the null hypothesis. So if we're rejecting the hypothesis that our time series is not stationary, we're creating a double negative, which means that we now we can reject the fact that it's not stationary, and by doing so we can say that it is stationary. It's a little bit hard to wrap your mind around, but basically if you get a p-value under 5%, you can reject the idea that it's not stationary and that you've done enough to the time series to make it stationary. If you didn't have that, then what we would do, of course, is differentiate the time series to assess and then reassess it with the augmented Dickey-Fuller test.
Let's say this line was a lot higher. The next step would be to differentiate the time series and assess the stationary statistic again. Using the shift method, we can just create a lag in our model and then retest it again. And what you'll get is something that looks a little bit like this. Now we've really made it stationary, but we've definitely thrown off some of the, the lag here. You can see the rolling standard deviation is a little bit ahead of it versus, it doesn't capture quite the height of these spikes here as it does in this one. But you can see the p-value is much higher than it was before, meaning that it could say that our time series is no longer stationary, but it was stationary to begin with. So regardless of what we're doing here, our line is stationary. And once we know that our line is stationary, we can perform ACF and PACF functions to understand the best parameters for PDQ. ACF is autocorrelation, as you can see here, and PACF is just partial autocorrelation. Again, I'm not going to go too deep into these two things. If you need me to, I can. But I think there are a lot of other YouTubers out there who can explain these far better than I can. But just know that this helps us choose the PDQ, and I'll show you how.
We're going to use autocorrelation and partial autocorrelation to find the P, D, and Q. And you can think of P, D, and Q as the parameter order for our ARIMA and SARIMA models. So what does P, D, and Q stand for? The P is the autoregressive term. The D is the non-seasonal differences needed for stationarity. You can think of that as the lag as well. And the Q is the number of lagged forecast errors in the prediction equation. So the Q is the moving average, basically. So we want to find those parameters because without them, it's very difficult to fit our model with the time series that we've created. So the way that we determine what those parameters are is using the ACF and the PACF, which just stands for partial autocorrelation as well as autocorrelation.
So when we plot this, we're going to use this to determine our moving average and our autoregressive parameters here. And we choose 1 to be the parameter for D because, as we saw here, it's stationary. And that determines our order when we go to fit our ARIMA model. And endog just means that the time series that we're providing is the endogenous data. And we fit it. And then what we're doing here is fitting the values of the ARIMA model to predict the levels. And we'll plot it. This is what it looks like. So the red line is the predicted, I guess, demand or the sales forecast here. We have a mean squared error. It's pretty high. It's 8884. Definitely not the best. It's definitely not taking into account the lows and the highs here as well as it could. And that's sort of to be expected. We're just showing it on the year 2010 here, by the way. And there's a lot more that we can do to tune this to be better. And we'll do the same process for the SARIMAX model. Excellent. So now that that's been fitted, we can redo it. And you can see here that our mean squared error is 6907. So a little bit better performance. And you can see that the red line is a little bit better in terms of finding where that average is. And it's definitely predicting where things are going up, where things are going to be going down. It's just not hitting the peaks as quite as we want to see to give us a lot of confidence that this model is working. So once we get this point, we can check the residuals. If this was working a lot better, which I'm sure certain items it would work better, we can go ahead and do a bunch of tests. The normal test is a great one. So we're going to plot the distribution. We're going to relook at the autocorrelation and the partial autocorrelation. and plot the frequency of those. And you can see here, these are the residuals, and this is the distribution of those residuals. And this is the auto correlation and partial auto correlation of those residuals. So you can see there's a few spikes where it comes out. Not too crazy, but it does come out. This is sort of the concerning graph here. Ideally, we would want these residuals to be much closer to this kind of normal distribution here with a much lesser frequency. But as you can see, this is what we get.
So this is something that took me a while to understand, but when we check for residuals, we're checking for what is left over after we've fitted the model. For many, but not all, time series models, the residuals are equal to the difference between the observations versus what we predicted. So it's that difference between our observation and predicted values. If we have a lot left over, obviously that means that our model is not performing as well as it will. And as you'll see, we do have a lot left over in this particular instance, but the main point that I want to get across here is that we are looking at a pipeline to do our time series analysis on. So even though in this particular instance, the product we're working with isn't working the way that, in a way that gives us a lot of confidence in the model, the procedure and the pipeline is what gives us that confidence that we shouldn't use this model.
So now we can do out of sample forecasting. In sample forecasting, we can just say, hey, let's take a look at this slice of our time series and compare it to what it looks like when we know what the real outcomes are. So that'll make more sense here. So starting at this point after 2011, we wanted to forecast, looks like most of November here. And we're definitely missing out on this giant spike here. But you can see that this is what the forecast looks like. Again, not super ideal. We're kind of getting an idea if this was a business sense and then this happened to us, that would be pretty catastrophic, I think. So obviously the out of sample forecasting that we take a look at here from this point on, this is what it looks like. And I think we can definitely do better. But we've done a lot of good work on this particular product to determine whether or not we could make a good ARIMA or SARIMAX. I keep saying SARIMAX. If you look at it, that's just what my mind looks at, but it's I'm guessing it's pronounced SARIMAX or something. But anyway, we can improve the model with exogenous features. So if you remember at the beginning of our video, I said that we would add in more columns here that will give our model a more robust understanding of our time series. So one way that we're going to do that is to include our date, years, the month, what if it, whether it's a weekday, what the day is. And when we take a look at this new data frame, we have our sales, we have our dates again, but we know that it's year 1 up to year 3. We know what month we're going to be in. We know what day of the year we're going to be in. We know, whether it's what weekdays it. So is it Monday, Tuesday, Wednesday, Thursday, Friday, et cetera, et cetera. So, but that's not all we can add here. We can add in holidays. And I just found this holiday data set on Kaggle, and it comes with dates. It comes with what holiday that date was on, whether it was a weekday, Sunday, Monday, Tuesday, Wednesday, the month, the day, the year. So we're really interested in these two columns here because we have something similar up here that's in a more vector-friendly form here. So one way that we can take these two columns, the way I did it was just rename the date to date, similar to our train DF here. And then we dropped the columns that we didn't want. And then I turn the date into a date time with the same format that we have in our previous data frame. And then this data frame comes with holidays dating back to 2004, which is out of the scope of our current data frame. So I just dropped the dates that we don't need, kept the dates that match with the same time frame as our other data frame, and then we merged them together. I also created a holiday bool, which just means it's 1 if it's a holiday, it's 0 if it's not a holiday. And then we vectored the month, the holiday, the weekday. And so we'll get like a bunch of different columns here. Yeah, we got 42 columns here. And it's like a true or false, whether or not it's on this month or not. And it even comes with whether it's a Veterans Day. It's not going to show me, is it? Veterans Day, Washington's birthday, President's Day, Easter. You know, is it a weekday, weekday 1, weekday 2? So we've vectorized the Tuesday, Wednesday, Thursday, all that good jazz. Nice. So now that we have this, we have our exogenous data, and we can move on and retrain, refit our data frame. So what I've done here is I've just split this into exogenous data that doesn't have the sales column, and then we've kept our draining data that does have our sales column. So, okay, great. So we can refit our model. Okay, so it's all fit. Let's plot it. And this is what you get. So yeah, the red line is the exogenous, and the yellow line is the endogenous, and the gray line is the ground truth. So certainly it does not capture these high peaks here. But as you can see, compared to our previous models, first, the mean squared error for both are much more, they are far more accurate than the errors we were seeing before we had done any exogenous work to the model. And you can just visually see that. It's capturing a lot more of the peaks and valleys where they should be. And so if you needed to get a rough estimate of where your demand was headed, this model would be good to use. I'm trying to think of anything else I need to do here to wrap it up. You do want to recheck your residuals. As you can see, the spikes here are far less. You can see here that the spikes were previously, when we checked our residuals, they poked out a lot farther than they do in these two. So we know that we've been making improvements. This is still a concerning graph. I think you would want this to be a little bit closer to each other to see that there was similar distribution, normal distribution. But anyway, this is to give you a good pipeline to create a robust model for demand forecasting. I'm definitely going to play around with this more to find a product that would work great for this. And if you have any questions, please let me know in the comments. I'm going to follow up this with several smaller videos on more targeted areas of this notebook. But if you enjoyed it, please let me know, and I'll see you in the next video. Bye.